Today, let's solve an integral from 0 to positive infinity. The product of two arctangent, ax, bx, over x squared. Now here, what if I just replace a with y, b with z, and come up with a function of three variables, x, y, z. So that is, if I have a look at this one, right? X squared, arc, tangent xy, times arc tangent xz, right? X, Y, Z, three variables. Now here we're going to examine the first order partial derivative in terms of with respect to y, right? df dy. Simply treating x and z as constants. Of course, I copied down this one also. Arctangent xz. This is also constant. So differential arctangent xy. So here we're going to have, of course, 1 over 1 plus x squared y squared. Then I'm going to remember x is a constant, a coefficient of y, so you just multiply by x. But this x and simplify with this x. We will have this one. Likewise, this time I'm going to differentiate again. So the second order partial derivative. This time with respect to z. That is, differentiate this one with respect to z. Of course, copy it down the bottom. X, y are both constants. And of course, then it's 1 over 1 plus x squared z squared. And remember, this time x is the coefficient of z, so I just multiply by x. But this x and this x, they can cancel. So this is all I have, 1 over this. So here I say if I integrate from 0 to b, for example, dz. Here's my integrand, is this one. I'm using this one as my integrand because now I can take advantage of the fact that this is the derivative of this with respect to z, as if it's a single variable of z. So what this definite integral does is that it somehow turns into just using its antiderivative, that is this one. And then you plug in b and 0, take that difference. That is, this is this antiderivative. Then you plug b into z, then you plug 0 into z. So arctangent 0 is just 0. So all you have to do is to replace z with b and use this one. X 1 plus x squared 1 squared arctangent bx. That's this definite integral. And so likewise, if I say, remember, this one looks pretty much like this one, except here I have z, where I have b in here. But since I can say if I replace this z with b, it'll basically make no difference, because as soon as I say f of x, y, b instead of z, right? So this almost the same, x squared arctangent xy times arctangent bx. Right, that's the only difference. And the only difference when I differentiate with respect to y is that for now we treat b as a variable as well, right? 3 variable also. So df dy, no difference. Right? So x plus 1 plus x squared y squared arctangent. Right? The only difference here is that previously I had x times z. This time I have x times b, right? I can say just for now treat b as a variable, right? So it's just a symbol. Here is z, there is b, right? So now you can say, okay, this is right. This is this one. So what if I do integrate from 0 to a, and I do dy, right? Previously it was dz. This time I say dy. My integrand this time, I'm going to use this one, right? Because remember, this is the derivative of this one with respect to y. That's why I say dy here. Right? If I use this as my integrand, I say I immediately have using its antiderivative. What's its antiderivative? Before I differentiate with respect to y, this is my antiderivative, right? Use its antiderivative, plug a into y, and then plug 0 into y. Take the difference, right? Arctangent 0 is 0, doesn't matter. So all you have to do is to replace y with a. Simply arctangent a times x times arctangent b times x. Right? So this looks like my integrand right here, right? So I also remember this one is also in the formula of definite integral, right? This one, I can use this one as also, right, from 0 to b on that one. So here, 0 to positive infinity. Then I say, okay, this time, right, for 0 to a first, right? The inside integrand is also another definite integral. This time, 0 to b, right? But 0 to b, I'm copying down this one. 1 over 1 plus x squared y squared times 1 plus x squared z squared. Right? Then first dz, no problem. Right? Then I do dy. Right? At last I do dx. So this time I just turned into a three-folded integral. Since I just did partial derivative with respect to y and z, so this time why not I do integral with respect to x first? I say, can I just, okay, outside I have integral from 0 to a, then 0 to b. Then first let me do integral from 0 to positive infinity. 1 over the same thing. Then I say do dx first, then dz, then dy. Right? In this case, it's totally justified, totally okay to interchange. So the reason I did this is because this time I can just use this rational function decomposition, right? Split it into two rational fractions. I say, here's the denominator, 1 plus x squared y squared. Right? The numerator, I can say a times x plus b. We're going to determine a and b. And we're going to say, okay, another one is plus this denominator. Then I can say c times x plus d. We're going to determine c and d. Then copy it down. dx, dz, dy. Right? So this time I say, okay, when you combine these two together, right, you have this multiply that. Right, 1 plus x squared z squared. Then you plus this multiply that. Right, 1 plus x squared y squared cx plus d. Right, it should always equal to 1. Right, numerator, right? Denominator, they're the same, right? Common denominator. So here's the thing. We're going to examine each term, right? Starting from the leading term, right? X cube term, right? What's its coefficient? Right? All you have, so you don't even have to expand in the first place. Let's just focus on this term. I say the only possibility that where it's going to come from is this times this, then this times this, right? Coefficient would be just, for now, we're going to just treat z and y as constant as well. Right? So you have a times z squared. The other one is c times y squared. Should always equal to 0 because you don't have any cubic term on the other side. Likewise, this term. The only possible way is that b times z squared. Right? The other coefficient is what? This times the d times y squared. Always equal to 0. You have no such term. X term, you have a. X times this, right? You have a. And then you have cx times y. Always equal to 0. You have the constant term. Right? What is that? B, D. B plus D always equal to 1. Right? So here I simply D equal to 1 minus B. Right? We can apply to this equation. I say B times Z squared plus 1 minus B times Y squared equal to 0. Right? Then I say easily B in terms of Z and Y should equal to Y squared over Y squared minus Z squared. Right? Y squared stay here, right? Negative by squared to the other side, positive by squared. This to the other side, negative bz squared. Now this time, right? 1 minus b. Right? B we know is this one. 1 minus b. What is that? Right? Imagine 1 minus this one. What is it? Negative z squared. Right? So what's A and C? I say, this tells me that C is negative A. But this tells me that when I say A times Z squared, negative minus A times Y squared, always equal to 0. Right? When you factor out A, Z squared minus Y squared, always equal to 0. But remember, Z and Y, they can change. Doesn't have to be equal to each other. Right? But it should always equal to 0 no matter what their values are. Right? So A must be 0 no matter what. Right? So therefore, C is also 0. Right? So we only need B and D. Right? B and D. So all I have to solve is this one. Right. First, I do dx. Should have nothing to do with y and z. They're just constant. Right? I can just factor out 1 over y squared minus z squared. Then I do 0 to positive infinity. Right. Then I say y squared over, I still have to copy down this one. Right, this one still is there. X squared, y squared. This time I have minus, right, minus. Right, this bottom is gone, is factored out here. So z squared 1 plus x squared z squared. Then I just dx, then dz. dy. So this time, all we have to work out is first integral with respect to x, right? Treating y and z as constant. Now, since they look very similar, right? All I need to work out this one, then this one will be obvious, right? So how do I work out 0 for positive infinity? Y squared over 1 plus x squared y squared dx. Right? I say this simply divide by y squared on both top and bottom. Dx. This time you just factor out this one. Then inside here you have 1 plus. This time you, beside x squared, you have y squared. Right? You just say yx squared. Dx. Right? So you flip this upside down, right? You have y squared. Right? Antiderivative of this one, right? Treating this one as a whole entity. They say arctangent, whatever that's in here, yx. Right? But to differentiate this one, it'll come out a y will come out. So you're going to have to divide by y. So this will become y. Right? This is 0 to positive infinity. Right? That's x. Right? Oh, here maybe I say I require a and b both positive. This time I say arctangent of positive infinity must be half pi. Right? So it becomes half pi times y. So likewise, this will become half pi times z. Right? So all I have to do is work out 0 to a, integral 0 to b. And this one, 1 over y squared minus z squared. That one I have half pi. Maybe put half pi here. In there I have y minus z. Y minus z. dz dy. But this one will simply become 0 to b, just 1 over y plus z, dz dy. First, dz, right? What's its integral? Right? Antiderivative, first of all, forget about y. Treating y as a constant, so it must be log of y plus z. right? Then z replaced with b, z replaced with 0. I take their difference. You have like a log 1 plus z. Z becomes b. Y plus b minus. This time, right? Log y plus z become what? Log y plus 0. Log y plus 0. I take that difference. Then you say dy. So first of all, this one combine. I say log. I could divide this over. Simplify 1 plus b over y. Say dy. Right, so what is that? Of course, integral by parts. Right? Even if you have a y at the denominator, doesn't matter. Right? Idea is the same. Right? So I say this u dv. dv is 1. This is u. Right? dv is 1. V is y. I say integral by parts. First of all, I have this, y times this one. 1 plus b over y. Y equals 0 and a. Right? That's u dv. V is y. V times u. Right? Minus 0 to a. U dv. Right? This time v du. V du. V is y. Du is differentiate this y. Right? Y times the derivative of this one. So I put this under here. I then differentiate this one. Right? We have a b up here. Right? Y to the negative 1. Well, negative. Y to the negative 2. dy. All right, this time. I say, okay, y times y to the negative 2. So y to the negative 1. Right? Multiply by y on both top and bottom. You have y plus b. This times y, you have 1 exactly. Right? Negative b. Negative, maybe you have positive right here. Right? So this simplify. So right now we have what? Right, this time. All right, I say plug a into here. A times log 1 plus b over a minus y becomes 0. Log 1 plus b over 0. Log positive infinity. Right? If it's 0 times positive infinity, but log positive infinity grows very slow. Right? You can use maybe L'Hopital's rule, right, to show that this undetermined form, right, still approaches 0. Right? 0 times positive, still approaches 0, doesn't matter. So minus 0. And so for this one, right, simply just b times log of y plus b. Then just y becomes a, y becomes 0. Take their difference. Right, log, first of all, right, like I said, log y plus b. Now this time y becomes a. Then y becomes 0. Then take their difference, right? 0 plus b, log b. behind. Half pi is outside here. So here, remember this half pi times a times, put this a on top of here. Right? And this becomes a plus b. I put a on top of here. And I say b times log. Right? Take it there, quotient a plus b over b. Maybe put this b on top here. Okay. So this time, what do we have? Right? Maybe combine these two. Right? I say multiply, right? First, a plus b. You just add up the power. Right? Down here, you have a to the a, then b to the b.